You're listening to MedX, the Medical Extrusion Podcast. Presented by U.S. Extruders. Extrude with confidence. Custom extrusion equipment designed for you and your application.
Hello, everybody, and welcome back to the MedX Podcast. This episode of the podcast will focus on laser processing, and our guest is Kevin Hartke, Chief Technology Officer at Resonetics. Resonetics is a global leader in advanced engineering, prototyping, product development, and micro manufacturing. Today, we'll be discussing some of the laser technologies available at Resonetics Lightspeed Lab for quick-turn prototyping of medical device components. Kevin, thanks for carving out some time to join us on the podcast.
Yeah, it's good to be here, Steve. Thank you.
Great. Before we get started in some of the technical dialogue, please tell us about the Lightspeed Lab and how it's used to support R&D programs.
Yeah, so the Lightspeed Lab is roughly 150 engineers, techs, and machinists that have about a little over 100 pieces of dedicated capital equipment across 10 locations and all in about 30,000 square foot of dedicated lab space. That whole team is really focused on supporting R&D engineers across the med device and advanced diagnostic space to quickly develop components and subassemblies. And so we quote turnaround time. We try to get quotes back to customers in 24 hours and projects, if we have material in stock, back in less than a week for straightforward kind of components. And the labs are a broad technical focus. So we have, laser processing, your laser cutting, laser welding, laser ablation. We have a whole wide range of laser tools available. We have expertise in nitinol processing, metal fabrication, electromechanical and fiber optic sensors, and microfluidics and batteries.
Okay, excellent. Let's get into some of the technical details and start with laser cutting. For an advanced delivery systems that require increased flexibility, torque response, and higher deployment forces, a laser cut hypotube is often used as the backbone. When working on a laser cut hypotube for an early stage vascular delivery system, walk us through the process at the Lightspeed Lab that allows you to optimize the hypotube performance.
Yeah, so we can start at a couple of points with the customers. So if you have no idea how to design a catheter, for an example, if you're a startup medical device company or you need very, very entry-level support on that design, we have our Agile product development team, and the Agile team will help you kind of start to finish to get that design developed and fabricated through the Lightspeed Lab. So they use our labs to quickly turn prototypes for a full-up functional catheter delivery system. If you have an idea of what you want for your catheter delivery system, kind of the anatomical path where you want to go, we start with a fairly qualitative approach. We have a defined process where we're going to pick up all of those qualitative inputs and turn those qualitative inputs into a series of patterns that we're going to cut across that catheter. And we've been advancing that technology through a variety of tools to kind of move away from the prototype, try, and repeat kind of approach to using more advanced tools like FEA analysis and the rest to inform those designs. So we're making some nice progress in that path. And so what we do is really just sit down with the R&D engineer. We get those inputs. We use our tools to get those inputs turned into a cut pattern. And then we're going to get that part cut and back to you for trial. Sometimes we hit it, squarely on the first try. Sometimes we don't. Sometimes, the customer doesn't know exactly what they want functionally until they get it in their hands. And so we just iterate through that process until we get to something that's functional for the customer. And then we will launch that into production along with their needs in terms of going to market. Okay,
interesting. So there's some cases where the customer might have a design in mind and they can simply send you a 3D model, right? You can do the cut pattern, or other cases where they give you the design input and you kind of iterate from there.
Yeah, the cut patterns are not they're a little complex to get through a CAD system. A lot of CAD systems don't like a lot of little cut interfaces, so they can get bogged down with that. So we don't really, it's not that you need to be an expert in laser cutting or what those patterns need to be. You just need to tell us, radius is a curvature, force function, kind of anatomical path. And then from that, we'll help you get the right pattern squared away and get that part in your hands.
Okay, gotcha. Thanks for that. Let's talk about the integration of miniature sensors and cameras to the tips of catheters. As catheters advance deeper distally into vessels, there's a need for spatial flow and force feedback to the physician. Also, camera prices have come down over the years, and you see more and more cameras integrated into catheters and certainly into single-use endoscopes. Walk us through the sensor technology platforms available at Resonetics and share how laser technology such as ablation and laser welding are used to integrate miniature fiber optic sensor and camera housings to medical devices.
Yeah, so we have two primary sensor platforms, an electromechanical approach, which is more akin to a flex circuit, if you will, kind of a strain gauge approach that we can get a lot of really good feedback, force feedback, torque feedback back to the proximal end of the catheter. And then we also have a fiber optic based approach. So, the fiber optic based approach has been deployed for a lot of applications out there in the catheter space. And it's low profile. The fiber optic is a few hundred microns or less in diameter. You can run that right up along either the tube or the wire that you're delivering the sensor with, and then get feedback from the end of the device. So you can get force feedback, torque feedback, and the rest from the end of the device. And so through both sensor platforms, it's a little bit of an engineering effort to get those sensors onto your device. So you can buy off-the-shelf sensors and you can, plug them into the end of your catheter and try some things. But you really, you want this combination of kind of low profile, optimum mechanical performance, and then getting anatomically where you want to be. So we pull all of that together, with our 3D manufacturing tools, micro manufacturing tools, to get the sensor where it needs to be so that it's going to function appropriately, get it, right out on the distal end if that's where you want it, so that you can get where you want with it, and then make it in a way that it's going to be designed and ready for manufacturing, so that you can put all this together and reach your price points that you're going to need to get to sell this as typically a single use kind of a device.
Right. Okay. Kevin, for a laser cut hypotube, you can vary the flexibility and the torque properties of the hypotube along the length based on the cut pattern. And for a composite catheter shaft that includes a braid reinforcement, you can vary the density of the braid along the length, proximal to distal. And you can also vary the durometer of the outer jacket materials from proximal to distal. For a wire component, is it feasible to use laser welding technology to develop a hybrid wire that takes advantage of the pushability and torqueability of stainless steel on the proximal end and the super elastic properties of nitinol on the distal end by seamlessly welding the two dissimilar materials together?
That's kind of the holy grail, right, of med device is laser welding stainless to nitinol. And I've, through my career, worked through patents in this space, through the Edison Welding Institute and the rest, to vet out these technologies. And there is some solid state bonding capability and technology out there to bring those two materials together. So we do have some familiarity with that. We've done some development on the laser welding side, and you can get 95% confidence, but you're not going to get the 99% confidence that you really want in that joint. So, there's options. You have options available from the mechanical standpoint as well. And then also just building out, more composite wire structures. One area that we use a lot as well to enhance flexibility and function is centerless grinding and machining. So we do a lot of work, very complex grinding to get that profile just right, so you can get the flexibility and pushability and everything that you want. And then if you need a machine feature function out on the end, either end, distal, proximal, we can help there. So we have experience with bonding nitinol to stainless. I would say that it's an area that is experimental at best, and there's some applications where it's gone to market. But really the most robust way and for nitinol these days is just to use nitinol and from distal to proximal, and then profile that part with the silence grinding or machining application as you need to. And the cost effectiveness of nitinol on the wire form is pretty good. So I think that usually works out pretty well.
Okay, very interesting. Thank you. Let's move on to laser ablation and laser drilling and start with balloon surface texturing. I know that laser ablation technology is used to texturize or roughen the outer balloon surface. For example, a micro texture to improve bonding of an electrode to the outer body of a balloon for an ablation catheter, or to potentially reduce the slippage of a balloon expandable stent during catheter advancement. Walk us through some of the micro texturing platforms that are used for balloons.
Yeah, so we use, Resonetics has a long history of integrating our own laser equipment. So we've got a lot of experience with a lot of different laser sources and, motion control platforms. We still use, for balloon processing, excimer technology. So there's not a lot of people in the industry that are still using excimers, but we find it as a really good tool set for doing large area processing of polymers. And the nice thing with an excimer is you have a lot of pulse energy coming out of the laser. You get a nice photochemical response with most of the polymers that you're interfacing with, and you can customize the beam to pretty much whatever you want. So, for polymers, for like a balloon, we could come in and these eximers are integrated into multi-axis workstations. We have workstations that go up to like 9 axes of control to really get the full 3-dimensional access to the balloon and do the processing we want to do. So you can go in and remove the neck area of a balloon to thin it down a little bit to make it more collapsible. You can drill discrete holes in the balloon if you'd like, from single microns up to hundreds of microns in diameter in any kind of array configuration that you might want. And then you can texturize the balloon. So you can go from kind of the nanoscale to the micron scale to create a custom texture on the balloon surface to do, as you described, increasing adhesion and decreasing slippage, these kinds of things. You have a lot of flexibility in that space. And we process, thousands and thousands of balloons on a weekly basis and have a lot of experience in that space. We've got a good technical competency there.
You talked about micro and nano level scale hole patterns, and I assume because it's micro and nano, it doesn't impact the integrity of the balloon.
Correct. Yeah, you always want to have a factor of safety in there. So if you are you're removing material, so you're not adding material. So you want to make sure you compensate for that in the balloon wall thickness. But it is microns and submicron structures that you're imparting. So you're not in any significant way going to impact the strength if you include that factor of safety in your design.
Okay, interesting. Let's move on to laser drilling of microscale holes in balloons or covered frames for embolic protection filters, which are devices that prevent embolic debris generated during interventional surgeries from flowing downstream, causing further issues. Recently, I had Elad from MetaBrain on the podcast. Fascinating discussion about some of the interesting process and automation technology that he's working on related to adhesion and joining polymeric covers to nitinol frames and stents without the use of adhesives or sutures. Walk us through some of the laser processing of micro-sized filtration holes to polymeric frame covers.
Yeah, so as I described, the excimer technology used for balloon processing, it's the same technology we use for these covered and coated frame structures. So we can, some of the filters we make, we'll start with the balloon structure. So we can literally start with the near net shape of a balloon, and we can, basically remove everything that's not the filter, right? So you can cut it to shape and then drill holes in it and basically get it to the filter, kind of profile that you're looking for. So The nice thing with the laser technology is I can dial that whole diameter in, like I said, from single microns to hundreds of microns. So you're looking for high flow, low flow, whatever you're trying to filter out, we have the ability to kind of dial in the whole diameter to support that specifically. So it's kind of a custom filter for the application space that you're interested in. So that's, on a balloon, we would start with a balloon structure and then drill in those holes and then cut it down to whatever kind of filter shape that you might want to attach to, typically to a metal frame of some kind. If you start with a metal frame and then coat it, you can do the same thing. So we can come in with that, and we've worked with a lot from Metabrain and know his technology well, and so he can come in with a very tightly controlled coating, and then we'll go in and drill holes where we need to in that coating. The key thing with dip coating, balloons tend to be a bit more consistent on wall thickness. That's a key factor for laser processing, because it's we're drilling through that wall to create the diameter of hole that you want. And so the consistency of that input material is very important. Alad's got really nice capability in controlling that thickness of coating that he puts down. But if you're doing standard dip coating and the rest, that we might have to look at that just to make sure that it's going to support the input material thickness and tolerances we're going to need to get you a good product in the end.
Interesting. So the thickness and uniformity of the wall of the cover is important. Does the different polymers, from polyurethane, silicone, expanded PTFE, PBAX, does the different grades of polymers have an impact on the laser processing?
There's a little bit of a dependency. Each polymer has its own, kind of photochemical response. So it's going to absorb, the ultraviolet light a little bit differently. We've got a couple different wavelengths. We work with 193 nanometers, which is, the lowest wavelength we work with, which has the highest photon energy. So it can ablate pretty much everything up to and including PTFE. And then you have 248 nanometer UV wavelengths that pretty much takes care of the lion's share of the polymers that we're going to work with. So there is a slight dependency on wavelength in the polymer that you choose, but pretty much everything in the med device space that we work with is going to work with one of those two wavelengths.
Okay. Hey, Kevin, this has been a real interesting conversation. Thank you so much for joining the MEDX podcast today.
Yep, it's my pleasure. Thank you.
Thank you for listening to MEDX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. All links are available in the show notes.